it's plus or minus or what. But first, give me the radius of this thing, or diameter.
The radius is A. A equals 6 centimeters. Okay.
6 centimeters, thank you. Go ahead. Now, what's the rotational velocity?
Rotational velocity, 1 revolution.
Clockwise or counterclockwise?
It's counterclockwise.
All right, so it's going this way, and this means omega is what?
1 revolution per second. So.
I will convert that in a second. All right, what else?
B is B naught in the AZ direction. Z is coming out of the page.
B is B naught in the AZ.
Yep, which is coming
out
straight out.
All right, so this is the B field. What is it? B? I'll just put a B naught AZ, okay?
B naught is 0.1 Webers per meter squared.
By the way, this was renamed around 1960 or so at Tesla in honor of Nikolai Tesla.
And then your resistance is 50 ohms.
That doesn't matter, but all right, 50.
It wants you to find the current.
All right. I assume it's this current, but I don't know.
That's the one that is assumed. Yes.
Yep. This is a classic physics problem from way back. Dr. Wentworth simply he took it from physics. So what do we have here? We've got V cross B occurring, right? Okay. Now, you remember back in the day, if you had something, and this was an anchor, and you had something moving at a velocity of omega at a distance r, moving with velocity of omega at a distance r away, and you wanted the actual velocity at this distance, right, where this thing's tethered. Think of taking like a golf ball, tying it to a string, or punching a hole through a golf ball, fixing it to a string of a given length and whipping it around. All right. It's got a certain amount of radians per second it's rotating, but if you wanted this velocity, it's just omega times r. Do y'all follow me on that, guys? The velocity at any distance r or away from the center is that. Now, if that's the velocity, remember, here we have a B field coming out, and we have something going counterclockwise. Now, you know that the induced electric field would be V cross B from motional EMF, right?
Yep.
Y'all with me on this? So now we'll be a little more exact. Since this thing's going counterclockwise, I'm going to say it's at a distance rho away. All right? Y'all with me?
Yes.
This thing is going to be going in the, and now I got to be a little more exact with my units, but let me just say this, okay? Just give me your eyes for a second. If it's going this way, right? This this rod's moving that way, right? If you take a look at this, V cross B is going to be an electric field outward. Do y'all agree with that? Just think about the common sense. Y'all follow me? If V is this way, B's out, E field's this way, right? Y'all with me?
Yep.
All right, now take a look at this. There's going to be a minus to plus voltage here, right? Work with me on this. Y'all agree?
Yes.
Now, what about here? What happens? I've got, now this V is this way, right? I got V cross B. The electric field is this way, isn't it? Can you all see this?
Mm-hmm. Yes.
You'll notice that the electric field induced on either this member or this member is pushing charge to the outer ring and taking it from the inner ring, if you want to think of it that way. Do you all agree?
Yep.
It means the voltage is going to be the same in these two things, and it'll have the same effect between this point and this point. Y'all with me? The way it's done. Correct, class? Yep. Do you see it? All right, think about it. Do you agree if you go on V here, cross B, the electric field induced here would be outward?
Yes.
Right? You see that?
Yes.
All right. Now, look over here at this point, conjugate point, same distance away. V is this way, right? All right. V, right, cross B would be this way, wouldn't it? Do you agree with that? All right, you with me? All right, now, here's the ground point, you might say. So from here to here, and here to here, same voltage. Do you agree with that? It doesn't matter about this one, does it? Or this one. As long as these 2 points are centered and touching. Y'all with me on this, class?
Yeah.
All right, so what's this amount to? Let's just do it this way. You all agree that V cross B, V would be in the azimuthal direction, cross B is going to be in the radial direction, or I can say this induced field, E induced, as a function of rho, would be equal to V cross B. Well, V is just omega rho, if I use rho as a measuring, right? And then it's going to be times B naught, and that would be in the A rho direction, volts per meter. Now that's the electric field. Everybody agree?
Yes.
You follow me? It's omega times, this omega times rho is really V cross B. V is omega rho, and B, and I got rid of I didn't do the A phi cross AZ component, but it will give you A rho if you do it. Do y'all follow me on this, class?
Yep.
All right, now if that's the E field, how do we get the voltage? Here you got to do the integration to get the voltage between the outer, which will be positive, and the inner, which is negative. And this is not going to be a function of time, so I just say it's equal to omega B naught, and then it's going to be the integral of rho A rho dot D rho A rho from 0 to A, because A is the dimension. And that one, I'll get out of your way. Omega B naught, the integral of rho D rho is rho squared over 2 from 0 to A, would be A squared over 2, and this would be volts. Now we can put the values in a second, but does everybody follow me on this? One thing we have to do is take omega here and turn it into radians per second. Now he has revolutions per second. And does everybody know there's 2 pi radians in 360 degrees of one complete revolution? So this becomes 2 pi radians per second. So now over here, that means this voltage in the outer ring will be between the inner and outer will be equal to omega, or 2 pi, right? Because it's 1 revolution per second, times B naught, which, what was it, B naught? What?
B naught was 0.1.
0.1. And then it's times A, which is 6 centimeters, right?
Yep.
So 0.6 squared, or, yeah, that's good enough. And then, what else do you got? Divided by 2. Anybody tell me what that is? You asked about it.
Oh, I got you. I got 1.13 microvolts.
What does he have?
I got 1.13 milli, but that might.
I mean, that's what I meant to say. That's what I was thinking.
Millivolts.
Yeah,
What
millivolts.
does he have?
I think that's what he
He has a current.
I don't know, he has to get voltage first then. Chase, are you with me on this one?
Yes, sir.
What does he have? Do you have the answer?
What, he just, I don't personally, but he
Okay.
has 22.6.
Microamps?
Yeah,
Good. What's our again, 50 ohms?
50 ohms.
So if that's clear, if it's, what did you say it was again?
22.6 microamps.
I mean,
Oh,
It's 0.06.
1.13 millivolts.
all right. 1.13 millivolts, and that means the current I would be equal to 1.13 times 10 to the minus third millivolts over 50. I don't know, but that's looking pretty good.
It's 22.6 micro amps. Yep.
All right, so 22.6 microamps. I'm going to ask a question 1 second. Everybody follow me on this? This is a straightforward problem. It just requires you to understand how to actually translate rotational velocity to linear velocity at points. Everybody with me on this? All right, now, question. Ready? Not in a book. Don't answer, just think. How do I get the power dissipated by that 50 ohm resistor? Now, think about it. Now tell me. Is it changing with time?
No.
What is it? I squared R, or V squared over R. Do you all follow me?
Could we also do VI?
Huh?
VI.
Sure, you could, but you know, I squared, nothing, it's DC. All right, so it's I squared R, take that I squared, multiply by R, or take V squared over R, or take V times I, either one. You're gonna always get, the power is constant, right? Where's the power coming from? You don't get something for nothing. there's an external force causing torque on this thing to rotate. It has to do that in order for this thing to work. If there was no external force, this thing would not go. It would, maybe if it was going at first, it would just slow down and stop because it's dissipating energy here. Y'all with me on this, class?
Yeah.
So if I ask for the amount of torque on there, I'm not going to, but how would you get it? Well, actually, you know power, right? So you know force, right?
Yes.
I mean, first, you know that if you knew the force, I'm almost going down the wrong track here. Yeah, if you think of, let me ask you. So we know that F dot dl is the differential energy, right? That's the amount of energy gained. If I take F, and I know that's the omega dl, just listen to me on this one, it'll make sense, right? If I wanted to know the amount of force required, what I could say is, if I knew that I had so much torque required per second, or so much force per second, the force times the number of seconds over here would be equal to the change in energy. I'm going to mess myself up here if I'm not careful. I'll tell you what, I'll come back to this one. But really what I wanted to tell you is this. All this power, it has to come from revolving this thing, right? Now the torque right there, it's going to be torque times omega will be equal to the power dissipated there. And you know how force times velocity is power? Do you remember that?
Wait, say that again?
Force times velocity is power.
That makes sense.
All right, for a given thing, force times velocity is power. Here, it would be torque right there. The actual, the torque times omega would be the force. And I'm going to come back to this in a bit. I'm just mentioning this to set the stage. In other words, any power dissipated has to be induced by some rotational force. It has to be. That's my real point. Okay, now back to next problem. You got one for me?
518.
518. It's the only
What's
other one.
one?
The other one you assigned for the homework after last class.
All right, hold on. I can tell you one thing about these problems. Most of them, when you cut through all this stuff, it's basic physics. There's nothing here that is that tricky. All right. Go ahead.
I got it. Unless you- here. A conductive rod of length 6 centimeters has one end fixed to the grounded origin and is free to rotate in the XY plane.
All right, let me go ahead and just make this an anchor. And this thing's going to have a certain length, right?
Yeah.
So rod with a certain length, L. And we'll call this X, call this Y. Go ahead.
XY. It rotates at 60 revolutions per second in the magnetic field of.
Clockwise or counterclockwise?
It does not say.
All right, we're going clockwise. Omega equals 60 revolutions per second.
Second, and the magnetic.
Go ahead.
And then the magnetic field is B equals 100 AZ millitesla.
Millitests are milliwebers per meter squared coming out of the board.
Yo.
So it's coming out of the board. He doesn't say if it's going clockwise or not. I mean, if the thing's going clockwise or not.
It does not, but he says find the voltage at the end of the bar. That's
So find the voltage between the two ends, right? Again, how many can see this one now?
Yeah, it's the last one.
All right, so how do you do it? Why don't we start by saying that omega needs to be in radians per second. We're going to do it the normal way, right? So let's go ahead and do this right. So omega here in radians per second becomes what? It's 2 pi times 60, right? So it's 120 pi radians per second, or about 377, that's omega. Now we've got to get the velocity at any point on the loop at a distance rho. You all with me? So if we're out, if this is the anchor, and we're out at distance rho, and this thing's moving with an angular velocity, omega, what is the velocity? Omega times rho, right? In the a phi direction, if you call it. You all agree with that? With me?
Yeah.
All right, now, that said, what's the next thing we need?
Just E.
E, yeah.
V cross
How do
B.
you get E?
V cross B.
V cross B, and this is induced field. Well, V is that, so I can put it as omega rho A phi. B, since he didn't even ask polarity or anything, it's crossed in the B field, which is equal to 0.1 AZ. That would be Tesla, or Weber's per meter squared, right? 100 milli. And it's cross product. What does it have to be in? A rho.
Could be A.
AZ has to be A rho. Do you agree
It's
with
gonna be
this?
A rho.
So this is going to be equal to omega rho times 0.1 in the A rho direction. And that would be volts per meter. Now, that's the induced electric field. And next step and final step, what do we get?
So voltage.
By
Just integration
integral
of
of
integrating
E.
that, D rho, right? So it's
Yeah.
rho. Now the voltage between the inner and outer, I'll call it E plus to minus, is the integral from 0 to whatever the length is. I'll just call it A, again, of this, which is omega rho times 0.1. And then it's going to be A rho dot A rho D rho. We could put the entire differential there, but the A phi and AZ dot to 0. That's the reason I only included A rho. And when I do this, I find out that I get 0.1 times omega, and then it's going to be times A squared over 2. Integral of rho d rho is going to be rho squared over 2, or A squared over 2. So that means the induced voltage is 0.1 divided by 2 times, what's A again?
I think it's 6 centimeters.
6 centimeters? Again?
Yeah, it's the same thing.
Wow. 0.06 squared. And omega in this case is going to be 120 pi. Right? That should be the voltage, is it? You asked me about it? I think you got it.
Yeah, that's it. It's 6. Yeah, that's right. It's 68 millivolts. That's the answer. But yeah,
Right.
that's
Now,
right.
these are for motional things. This is, go ahead.
So if you assume a clockwise direction, would that put the plus side of the voltage, or that had the E field flowing inward, right?
Well, I'm gonna do it from here. We're assuming B field outlet board.
Yeah.
Then take a look. If we go clockwise, this one, or kind of, you said clockwise or kind of?
You went clockwise, just
All right, if I
mean
go clockwise, then this is going V this way, right?
Mm-hmm.
V cross B out of the board going this way, right? If it was counterclockwise, it would go the other way.
That makes the voltage higher at the center of the bar than the outside.
Yes, this would be larger than this potential.
Okay, just making
If
sure.
you actually had a way of tying a resistor to this, current would flow from here to here.
So in the problem, if he defines the origin as being grounded, then it would have to rotate.
It doesn't have to rotate anyway. He can tell you to rotate one way or the other. It doesn't
That
matter.
would just make your answer positive or negative.
Yeah, but ground is just a reference point.
Yeah, I know.
It doesn't matter.
It's just 0.
Yeah, that's exactly it. Everything's measured with respect to it.
Yeah.
All right. Anything else?
No, that's it.
I want to mention one thing. Remember, closed loops, right? you got closed, for instance, if this is a current, watch, watch. If this is a current, and I had a bar like this, moving this way, just think through, what would the voltage be? Well, the B field's into the board. Do you agree if the current's going up?
Yeah.
Right where the bar. So if I have V, right, cross B, the voltage would be upward. Do y'all agree with that?
Go.
If it's V cross B, B field would be into the board. You agree with me there because the current's up? Yeah, right? What about over here? If I have V here, which is the direction of the B field, out of the board, right? So if I have V that way, this would be the direction of the E field. You all see that?
Yep.
Making sure you do, right?
Yes.
Now, if I had another bar here, moving with the same velocity in this direction, which this is the E field for this one, what would the E field for that one be?
The same direction.
Same thing.
Just lesser
Same
because the
direction.
B is.
Y'all with me on this? I want you to keep watching. All right. Now, what if I connect this, make it a loop, and put a differential cap there? Now, question is, we got the E field, the voltage here, the voltage here. What about the voltage on this segment?
It's just zero.
I got V going out, cross B. Well, it's perpendicular to the actual length. Do you agree with me? Right?
Yes.
You guys paying attention?
Yeah.
In other words, if it's going this way, V crossed B, either way, is a perpendicular. When you integrate this over the length, you get zero, don't you? And you get a big yawn. What about down here?
It's equal and opposite. Zero.
Same, it's zero, right? So if I connected a loop, like so, and I asked you for the differential voltage there, based on what we just said, what would it be? It would be this voltage causing it to go clockwise minus this voltage that's causing it to go counterclockwise. You all with me, class? In other words, by finding the individual induced voltages here, you could find the voltage induced on the loop. You all with me?
Yes.
Now there's another way to do it. Do you all follow me on this? This is the B field is constant. If this thing was moving, you could do it another way. You could integrate the B field dot ds over that entire closed loop, right? It would be a function of time though if this thing was moving out. Do you all hear me on this? Right? And then you could take a time derivative and in fact you would get the induced voltage. You all with me? And by the way, the B field could be varying with time. That's a little bit more work. But if the B field's varying with time, then you would have to do the integral of B dot ds around that closed loop, and you would have to have an equation for the amount of flux through there versus time, if this current was, say, a function of time, as well as, the B field would be a function of time and position, then you'd have to take a time derivative of the whole 9 yards to get the induced voltage. You with me? I'm making that point for a lot of reasons. I want to make sure, come final exam or quiz, that we are clear about that. A way you can never make mistakes. If the B field is time varying here, because I is time varying, then you have to do an integral of the B over the area, and the area is a function of time. Then you take a derivative of that to find the actual induced voltage. By the way, if there was more than one term, what would you do?
Multiply it by n.
N, right? Okay, good. And I didn't give you any transformer problems. I apologize. But I think, I was thinking about that. It's probably better I don't delve into that because Wentworth just hand waves the thing in this book. There's one problem that just has to do with reflected impedance. Do y'all remember that? So I figure I might as well not go too far afield from his text, even though I kind of want to. All right, other questions? What?
Oh wait, no.
Oh, okay.
I don't know why not.
That's all right. I mean, you understand this without
Yeah,
usually
yeah.
asking. Okay, you guys got it? Now, I'm going to go to the next part in your book. And this is
The lossless template?
No. We did displacement current, remember?
Yeah.
Now we're going to, lossless TEM waves.
Where's
Now,
5.5?
I don't know. What happened to it?
There's just not any
What is
problems for it.
5.5?
What is? Is not. And yet it is again.
Maxwell's right.
Yeah, well, I put that up.
Yeah.
All right, guys, so here's where we get into the beginnings of EMAG 2. This is all time varying now. And a lot of this stuff was time varying we talked about, but it had to do more or less with either something moving through a magnetic field that was spatially constant, or it had to do with a loop that's fixed, a time varying magnetic field. Now we get into the whole nine parts. But next week is our last week of classes. We're doing great. A lot of times, people are way behind.
So we're gonna finish this this chapter and then
Oh, yeah.
do a little bit of the next, and then we'll be
But
done.
they kind of open up.
Okay.
The way I do this is, I start with, we're assuming these things are known, and they are. Maxwell's equations are one of the few things that everybody has confidence in, and nobody even thinks about questioning. There are a lot of things that people question, but this isn't one of them. So curl of H is equal, now I'm going to start here. You don't have to write this down. That's J, not D. So curl of H is equal to J plus the partial of D with respect to T. That's the first one. The second one is curl of E equals minus dB dt, right? Okay, then we have these coupling equations. J is equal to sigma E, and we have D is equal to epsilon E, and we have B is equal to mu H. Both this equation and this equation have mu relative and epsilon relatives times some mu naught epsilon naught that is a free space. You all with me on this class? So now I tell you, he doesn't do it all the time this way. In his book, he does it sometimes this way. I said what we want to do is start examining one equation with one unknown and seeing what this thing dictates is going to happen. It's going to be wave phenomenon, probably getting wave phenomenon. So we start by this. We use these assumptions and we put them in here, and we do one more thing. I go to the phasor domain, so anytime there's ddt in the phasor domain, it just brings out j omega. Do you all remember this? When you had circuits, remember? An inductive reactance, technically what? The voltage across the inductor was LdI dt, but when you assumed sinusoidal behavior, e to the j omega t, it became j omega times L times V was equal to I. Do you all remember this, class? So basically LdI dt is j omega times L I is V, or the inductive reactance V over I was j omega L. I'm just going to say that we remember that, don't we? So here, now I take this equation, I break it down. I did this before, but I want to just do it with you. The J becomes sigma E, so I'm going to take the sigma out of front. And then D becomes epsilon E with a time derivative, becomes J omega epsilon times D. This is one equation, and here I've done something. I've gotten rid of both J and D. I'm in terms of H and E. Everybody with me? Now the next equation, curl of E, that's equal to minus dB dt. B is mu H, the ddt just brings out J omega mu times H. Y'all follow me on that, guys? Now I want one equation with one unknown. How many remember me doing this? Okay. Now, one equation with one unknown. There's two possibilities, either H or E we could use. If we wanted H, we take a curl here. Then you have curl of H would equal, and we're assuming epsilon, sigma, and mu are all not constant, not spatially varying. If they spatially vary or time varying, things change abruptly. But for this one, if they're not spatially varying, then I have curl of H, that's a constant. Curl of E, I can replace the curl of E with this. And now I have one equation with just H. The classical way to do it in terms of electromagnetic propagation is take a second curl of that I did. So, and this is, you know, and some of you may have seen this in physics. Did you have honors physics here? Anybody?
Engineering physics, I don't.
Don't they have an honors versus non-honors physics or not?
They do.
They do?
No, I'm asking you. I don't know.
I thought they did.
Yeah, I
Because
think I do.
What? They do. And honors physics, you might get this. If you didn't take it, it's not a big deal. But So if they do, then you would take curl of E, that's this, double curl of there is equal to minus j omega u curl of H, right? What do we do to get rid of curl H, guys? Take that curl of H and stick it in there. It's equal to nothing but a bunch of constants in E, right? So I come here and I say, that right there, I should have put an equal sign. And by the way, curl of E is actually equal to the gradient of the divergence of E minus del squared E. This is one of those vector calculus things. Did you have this or not? You probably didn't. If you didn't, if you have no reason to know it, you don't know it. And this is equal to minus j omega mu times the curl of H. Well, there's the curl of H, which is sigma plus j omega epsilon times E. And lo and behold, now we have one equation with one unknown.
Wait.
What? Ask.
So is the okay, so this Laplacian, the del squared, but what's del? What is that?
No, it's the gradient. This is the gradient of divergence of E. See, curl of E is going to be the gradient divergence of E minus del squared, which is Laplacian of E. Now, something I got to tell you, is this in the book anywhere or not?
Laplacian.
Not Laplacian, but the this proof that I'm doing.
No clue.
It might be in chapter 6, but don't worry about it. It's got to be somewhere. It's probably in chapter 6. This is classic. And by the way, everybody that goes through engineering or physics, for any event, they go through this like with a fine tooth comb. At a good college. I suppose you can go to, I don't know, what is that thing online? University of Phoenix. I mean, I shouldn't cite these things as bad, but I've heard some stories about the online degrees worth about the paper they're printed on, because there's no real way to hold people to standards in a lot of cases. Now, good online programs do it with testing facilities, but that's sort of my impression from what I've heard. Okay, you ready, guys? You all agree this is one equation with one unknown. Here's what we're going to do now. Pay attention. This is important. First thing, we're going to assume charge-free. A charge-free region. What does that imply? What is charge? What's the symbol for charge density? Rho v. What up here might be affected by that? Take a good look. Right here. Divergence of D is rho v, right? And that means divergence of E is rho v over epsilon, correct? So that means we assume this goes away. You got me on that, guys? Now again, that works pretty well in almost all environments that aren't highly ionized. You can assume it doesn't have a net charge density. You know how when you propagate through the atmosphere, we can assume there's no real net positive or negative charge of any bearing as any consequence. You okay with it? Next thing over here, I'm going to come and do this right here. Now we're going to start getting into the crux of it. So I'm going to take this equation. I have minus del squared of E, and then I have equal to this. Now, this is equal to minus j omega mu times sigma plus j omega epsilon times E. And here we create a new constant. I want you to write this down. This is in chapter 6. It's I think, alluded to in chapter 5, but I want to make sure I say this. We create a new constant. We say gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. This is gamma. Do you remember gamma being a symbol we used when we did transmission lines? Guys?
Yes.
All right, so what is gamma? Gamma is equal to
Is this the same gamma?
alpha plus j beta, same actual units, but it is taken from the actual properties of, it's not the LC and R and G of, remember that? Those are
Yes.
lumped element or bulk parameters. This is for the actual differential parameters, or they're really, it's epsilon, mu, and sigma, which are the point parameters. They're functions only of where you are in space. They have nothing to do with the dimensions or the geometry. Y'all follow me? Resistance would, and so would inductance. Yeah, you know, a coax cable of different radius and stuff. All right, so it's alpha plus J beta. Now this is called the propagation constant. Anybody want to gather what this is?
Attenuation.
Right.
And then the wave number?
Next one.
Wave number?
Yeah, right. This attenuation constant, the units are Napiers per meter. This is called wave number. And its units are going to be radians per meter. Radian is a unitless thing, same thing as a Napier. The units agree, so that's gamma is equal to that. So that means that equation, and now I come over here. This is one of my area, my PhD was done in really in simulating electromagnetics. Transient electromagnetics are a big deal to me, and it's much harder to do some of those things correctly, but this is of interest to me. So anyway, now I get this. I have minus L squared if E is equal to minus gamma squared. You all see that, class? Right? Because I've gotten rid of that, all those constants, J omega mu sigma plus J omega epsilon. With me, class? That's that top equation right there. I've taken and gone here. Now, the next part is kind of straightforward. You all see how what I can do is take this to the other side and set it equal to 0. So I'm going to do it. Equal to 0. All right, we've assumed so far that we have charge-free region. That was the extent of the assumptions. Now here comes the next assumption. And here's where you write down plane wave propagation. Now what is a plane wave first? Before I'm going to modify this so we talk about only plane wave propagation. All right, I want you to think about this little case I'm going to give you. If you have a rock and you drop it into a puddle, we're going to say the rock is analogous to an impetus, some kind of a forcing function electromagnetically. If you drop it in the puddle, ripples occur, and they start going out radially from that puddle. You with me? All right, well, if you have an antenna and you turn on the transmitter, electromagnetic waves will flow out at a given frequency radially away from that antenna. Just follow me on this one. Now, if you get far enough away, like if you drop the pebble and it's here, and you froze time, you could see that there would be something that would be cylindrically symmetric as far as the heights of the crests of these things. They would be moving out. There would be a minimum, there would be a maximum, and you get wave motion. The heights would vary, but the velocity would be always outward. Can you all follow me on that? Now, if you get far enough away, all of a sudden, this thing has a radius of curvature that's looking like it's infinite. It's looking like there's no curvature to this thing. You all with me? If you get far enough away. Matter of fact, ocean waves that originate like thousands of miles from a shoreline, when they come in, they look like, if you look down the crest, it would be a straight line as far as you could see. You all with me? Because the event that caused them was so far away, the radius of curvature is basically infinite. Your eye couldn't detect it. With me, class? Now, if that's the truth, if you come out here, just think with me for a second. If we looked at the wave, the crest of that wave, looking something like this, it's flowing this way, then if there would be no variation in this dimension. Do you all follow me that way? If we're talking, it's going that way, we'd look at the derivative of the actual height versus the position would be 0 in this dimension. And if we allowed ourselves to imagine this wave not being confined to the surface, but say this was a giant cylinder where there was a center perturbation, it would not be a function of either the dimension this way or the dimension this way, perpendicular to the direction of propagation. You with me on this, class? It's important at least you appreciate what I'm saying. You get far enough away from an event, basically you have something that looks like it's moving only in one direction and it's planar. That's the idea of this. So, coming down to this thing, what they assume in Dr. Whitworth's book is this. We're going to assume we're very, very far away from whatever causes wave. By the way, this agrees with all observations. Long away from an event. Then what happens is this derivative itself, the actual, just listen to me, don't write this down. When you take a look at del squared of E, E in general has three components. With me, EX, EY, and EZ, Cartesian. Well, generally that del squared is second derivative of X with respect to, and this would be EX plus EY, and EX AX. Wow. EX AX plus EY AY plus EZ AZ plus the second derivative with respect to y of all this stuff again. And I'll just call this vector E. And then plus the second derivative with respect to z of vector E again. In general, there's 9 coordinates. Do you all see that? You're going to have an x, y, and a z coordinate. There would be 9 coordinates after you do this del squared. You all follow me? You're going to have 9 components. You're going to have 3 on each coordinate axis. You with me, everyone? Then you have to do this part, which is going to have all those again. And you're going to get 3 differential equations, each with 3 variables in them, and it's a pain in the butt to solve. Got it? That's the upshot. So what we do is this. We're looking at only plane wave propagation. This part you need to pay attention to. I'm going to erase this and tell you exactly what the problem is. And as some of you have probably gathered, I'm interested in this. So back to this thing again. Now we assume this. We assume we're far from the event that caused it, and the wave itself is only propagating in the z direction. So that means the velocity of the wave is only in the z direction. It's going that way. With me? And it also means if this is the x-axis and y would be out of the board, that the partial of the electric field with respect to either x or the partial of the electric field with respect to y is 0. So I haven't defined which orientation the electric field is, but I'm going to give you a clue on this one. Anytime you have an electromagnetic wave that's propagating, the E field will be perpendicular to the direction of propagation. You all with me on this, guys? It will, and I can prove that in a bit, but you're going to have to accept that as fact. So if it's propagating in the z direction, you have an E field that could be in X or could be in Y. In Whitworth's book, he takes it in the X direction. All right? So we're going to assume that the E field itself, that we're going to actually solve for that equation, is only going to be in the Z direction, the X direction, and it will only vary with Z. Just bear with me and you'll see what I'm up to. So I'm going to assume the E field itself will have some E naught, and it will be in the Z direction. I'll call it a function of Z. Matter of fact, I'll just call it E of Z. I don't have to put anything more than that. And it's going to be in the AX direction. So it's oriented in the X, propagating in Z. Can you follow me on this? Now the next part, I'm doing this to try to make it, may not be that obvious to you, but you're going to see where I'm going and why I'm doing this in a second. So if I do this, and I take this equation, now, you know how normally you're going to have second derivatives with respect to x, y, and z here? Can you all follow me? Because it only has a variation versus z spatially, it only varies with z, only the z derivative will survive. So you get this. This is in chapter 6 if you're looking. Second derivative of ex with respect to z squared minus, and it's going to be gamma squared, EX equals 0. let me just leave it like this, and you'll see this, all right? It's only gonna have an x component. We can multiply this whole thing by ax, but it doesn't really matter. Okay? Now, at that point, that's a first order differential, or second order differential equation, and it's homogeneous. You know, how would you normally get a solution to that, by the way? If you had, say, just that equal to 0 and gamma squared was a constant, how do you solve something like that? Well, Laplace transforms is typical, right? You could take a Laplace transform of this. X would be like the time derivative, or the time function.
Yes.
And you would get what? S squared outside here times E of S, and there would be minus S and E of 0 and all that. But if you assume it's steady state, it would be S squared out here. This would be simply minus gamma squared and times E of S. Take 1 over that. Then you would do the inverse Laplace of that, and you would end up with two exponential functions. You could solve it with integrating factors. Did you have to do that back in the day? At the end of the day, and Wentworth, I think, does this he introduces a integration, or I should say a differentiation factor, and does the derivatives. But at the end of the day, here's what happens. This is in chapter 6. E of x will be now write this down, E naught plus times e to the minus gamma z plus E naught minus e to the gamma z. Just write that down, put a star on it, make sure you don't forget it. This is the x component of the electric field that's propagating from some event that's a long way away, and it's going in the z direction. That's the solution to this differential equation here, assuming it's charge-free and we're a long way away, and the E field is in the x direction, okay? Now hear me on this part. I'm almost done. Ready? This component is in the plus z direction. It's propagating the plus z direction. This component is propagating the minus z direction. I'm just showing you the direction they propagate. If you wanted to find the time domain form of this, then you would say Ex as a function of z and t, and the time domain would be equal to the vector. This is actually a vector phasor, but don't worry about that. Would be the real part of e to the j omega t times e, going to be vector phasor here. Now I'm doing this for a reason. Remember I talked about going from time to frequency domain? I did some time ago, I did that I think with transmission lines, right? All right, what actually happens here? Well, if you take a look at this, I'm just going to do the positive going away. I'm going to do it right here because I know I'm running short on time. So I want you to watch this because it's not tricky. If I take the real part of that, it's really the real part of e to the j omega t, and then I have E naught plus, and it's going to be e to the minus alpha z, and it's times e to the minus j beta z here. Y'all with me? I'm just putting in here, gamma is alpha plus j beta, right? Are you guys with me on this one? All right, now expand this. This is what the E field would be in the positive direction, moving in the plus Z direction, the EX. All right, it's the real part of, now just look at this. E naught is a scalar, that's a constant. Then it's going to be e to the minus alpha z, and it's e to the j omega t minus beta z. Can you all follow me on that? I simply stuck in that definition. I mean, I basically got ahead, I've grouped terms, so that anything with a j in it, exponential, I've grouped. Now, the real part is the real value. So E naught plus is just the real value. E to the minus alpha z is simply going to be, that's strictly real, because alpha is real, z is real. And then what's the real part of this? What's the real part of e to the j theta? Think about it.
The cosine part.
That's right. And this becomes simply cosine of omega t minus beta z. Now, that dictates a plane wave traveling in the plus z direction. As a matter of fact, if you expand this and take it to the time domain, then you're going to get E naught, write this down, E naught plus e to the minus alpha z times e to the, and now you're going to get just time domain, it's going to be cosine of omega t minus beta z ax, and that's a wave traveling in the plus z direction, and it's going to be plus E naught minus e to the plus alpha z cosine of omega t plus beta z ax. And that's a wave traveling in the minus z direction. Can y'all follow me on this? Now I put that down.
Over there. Is that is E of x down there at the bottom? Like that equation?
Yes,
E of
this
x?
is E of x, but it's in a positive direction. I only did one part. If you take this whole thing and multiply it by e to the j omega t and take the real part, then you're going to get what I put there, those two terms.
Omega t plus beta z.
Yeah, and that's how you always tell what direction it's traveling. Look at this argument. That's constant phase, right? I mean, the argument of cosine's got to be an angle. So it's constant phase. If you look at this and track this, I'm going to do this for you. You remember phase velocity? How many do? The term, at least. How do you always get phase velocity? You take a derivative phase with respect to t, right? I'm going to do it right here. I'm going to stop. So if I take a derivative of phase, which is omega t minus beta z, with respect to t, what happens? I get omega, right, minus beta times dz dt equals 0, right? Y'all follow that? Just take a derivative of these things. Derivative of omega t with respect to t is omega. Derivative of beta z with respect to t is beta times dz dt. What did I tell you about dz dt? Isn't that a velocity? Time rate of change of position. Suppose dx dt, it should ring bells. Physics, right? Velocity. This is the phase velocity. Now take a look. Omega on the other side, I get phase velocity equals dz dt, right? That's equal to omega over beta. You'll notice it's positive. That wave, and you can plot this, just plot a few instances in time difference, and then plot it spatially. You'll see the head of that, the crest moving away, or the top one. You with me, class? All right, I know you want your quiz, so I'm going to give you your quiz now. How about this, guys? First row, fill it up. So you can move there. This row, fill it up. This row.